Good afternoon, everybody. My Earth Sciences, dealing with cultural heritage, conservation of cultural heritage from Sapienza University of Rome. My PhD project is mainly focused on the conservation and adaptive reuse of massive buildings, especially belonging to the ensemble of war heritage. So we know that historic massive concrete buildings can suffer from weathering issues, mainly due to a combination of factors, among which recurring changes of temperature and relative humidity, the exposure to direct precipitation and the runoff of moisture, as well as the attack of acids and salts. According to the European standard EN 16682, published in 2017, moisture content in cultural heritage and immovable cultural heritage can be measured through relative methods, among which electrical capacitance and microwave meters can provide real-time readings. They are not invasive or destructive because they simply need to be put in touch with the surface to be measured, but they can lead to some misreading and misinterpretation when there are some interfering elements, such as the presence of salts, especially if in the liquescent form, or metal reinforcement within the surface, or also physical heterogeneity, such as the presence of surface exposed fractures. So the main aim of this research is to try to understand the real capability of relative methods, and specifically electrical devices, for moisture content measurements in surfaces that are aged and deteriorated. The case study is the huge concrete bunker that was built by Germans during the Second World War occupation of Norway in 1941. It is located in Trondheim in Norway. These are its large dimension, as you can see, outer walls of almost 3 meters thick. And as you can see from these pictures, the building is currently affected by a significant decay on the external reinforced concrete walls. That is mainly due to the coupled action of salt and weatherings, salt and frost weatherings, very likely to happen in the Scandinavian climate. These are the instruments we chose to conduct the monitoring campaigns, microwave and capacitance devices. As I say, they are relative methods, so they can be useful to have the information about whether the moisture content in a certain point or at a given time is different from another, but without knowing the actual difference in absolute values. They also have different penetration depth, since they work at different frequencies and according to different measuring principles. We know that the microwave meter can detect moisture up to 30 centimeters, while the capacitance one up to 4 centimeters. These are the areas that we chose. First of all, a very exposed outdoor area that is located at the corner, at the southeast corner of the bunker, and then an indoor area that has been exposed to outdoor conditions, but then in 2005 was incorporated into a new build construction that is adjacent to the bunker. So it has been exposed to indoor conditions for 19 years. And both of them are, as you can see, salt damaged and also have superficial fractures. Measurements were taken according to a predefined grid with a spacing of 20 centimeters, and 3 measurements were taken for each point and then averaged to obtain a single final value. First of all, data were normalized into a 0-100 scale, and then moisture content isoline maps were created to display the moisture content spatial distribution by using the radial basis function interpolation method, as you can see from this example. And also the surface salt accumulation was visualized by using a thresholding-based image segmentation to create binary images where the salt accumulation coverage has to be clearly visible. So we obtained a multi-layered information by superimposing the original image plus the salt accumulation coverage and the moisture content spatial distribution. Then we evaluated the moisture content anomalies with respect to salt accumulation coverage. So first of all, we computed the normalized moisture content anomaly, where moisture content is the normalized moisture content at each grid point, and moisture content mean is the average of the surrounding points. And also the percentage of white pixels with respect to the black ones in each quadrant around the grid points, and then normalized again in a 0-100 scale. So here you can see the outdoor scenario with the moisture content spatial distribution superimposed to the salt accumulation coverage, and both microwave and capacitance devices detected higher moisture content, around 80% in the lower right part of the wall. And this was where salt accumulation was, and this was probably due also to a possible rising groundwater as we were measuring at the ground floor, and also to the exposure to outdoor atmospheric precipitation, since we are exactly at the corner, as I said before. At the same time, in the upper left spot, both devices recorded the lower moisture content values, although the wall is still covered with salt accumulation. And here the salts are in a completely crystalline form, and with such thickness and irregularities that causes the signal to be lost. So we can say for the outdoor scenario that the consistent rainfall in Trondheim can represent an active moisture source that can easily penetrate the material from the outside. While the indoor scenario is pretty different, since we know that the conditions are very different. There are some radiators nearby the wall, so we see and we know that the surface is dry, since these radiators are regularly turned on for human comfort. And in fact, the moisture microwave device can generally detect the lower moisture content values because the wall is well isolated from the outside, while instead the capacitance meters can still detect some higher readings in some specific spots. But we know that daily indoor temperatures can lead the moist air eventually present within the fractures to evaporate, and this can lead to subsequent salt accumulation on the surface. So the capacitance depth penetration that is 4 centimeters might not be enough to detect such residual water that could be in the first layers of the wall. Here we have the percentage of white pixels versus the normalized moisture content anomalies for both the outdoor and indoor scenarios, and for both capacitance in blue and microwave in red, where the light blue and pink areas are the range between the 25th and 75th percentiles. So we assume for this case that the data that are falling outside this area are representative of more significant anomalies, and the table reports the number of occurrences of data falling above the limit of the 75th percentile and below the limit of 25th percentile. Here for the capacitance device, we can see, we can assume that for positive anomalies, this could be due to actual moisture content where the wall is exposed to atmospheric precipitation. And this effect is especially enhanced when the salts are present in a deliquescent form, as in the 1.9% of cases. While in for negative anomalies, this could be due to the uneven contact surface that is due to the presence of surface exposed fractures that can affect the detection. The indoor scenario is different, since we know that the wall is dry, so the capacitance could be unable to detect the water-filled pores that are eventually present at the subsurface level. So the higher readings, the positive anomalies we see, can be due to the presence of conductive elements below the surface. And in the case of negative anomalies, again, possible detection issues are the presence of such irregularities on the surface. The microwave device, when we consider positive anomalies, the presence of moisture in the inner wall layers can be, of course, responsible in the outdoor scenario, since we have said that the wall is exposed to the atmospheric precipitation, while the negative anomalies in this case are even more due to this uneven contact surface, since the sensing element of the microwave meter is even larger than the one of the capacitance one, that is a spheric conductive plate. For the indoor scenarios, here the microwave meter can be able to detect the same residual water as before, but this time could be detected by the microwave due to its greater penetration depth than the capacitance meter. Negative anomalies, again, can be due to the same reason as for the outdoor scenario. So in conclusions, capacitance device can experience detection issues indoors, since when the surface is dry, data can be noisy and not fully representative of the actual moisture content. And so it could detect the possible presence of residual water, but that is at the limits of the device's detectable depth, and eventually be affected also by the very thick salt layers and the inner metal reinforcement. While positive anomalies recorded by the microwave device can be due to active moisture source, but also to inner metal reinforcement, while negative anomalies could result from irregularities affecting the detection capabilities of the instrument. So finally, the presence of interfering elements should always be considered when interpreting moisture content anomalies, and in order to avoid incorrect conclusions about the conservation state of historic materials. Of course, the dataset of this work is limited, both in size and in diversity, and also the interfering elements I described can heavily affect the detection and also the interpretation of data. So this preliminary work will be followed by further developments that will include the use of advanced data analysis to identify patterns in the moisture content anomalies, but also a comprehensive calibration of the development of a comprehensive calibration protocol under controlled conditions to better understand how readings from moisture devices really correlate with the actual moisture content of historic materials.